Okay, so Sites is trying to figure out what kind of alarm this is and why it keeps going off. If you remember, it went off at the end of class on Tuesday, and apparently it went off yesterday as well. Somebody tried to go through a door, somebody left a box open, somebody forgot to push a button, somebody pushed an extra button. Hopefully this will shut off in a few minutes. So I want to start actually getting into the guts of the course. And what we're going to be spending a fair amount of our time on this semester, especially in the first few weeks, is talking about simple algorithms for manipulating strings. And really, I want to think of it even at a more basic level than simple algorithms to manipulate strings. Instead, think about them as simple machines to implement strings and useful formalisms for talking about strings and functions and sets of strings. And so I have to start sort of at the ground with the, thank you. With the sort of mathematical equivalent of what in other departments is this is a transistor, and when we start from transistors, we build up gates, and once we have gates, and we can build up flip-flops, and once we have those, we can start building multiplexers and CPUs and cache lines and Facebook. So I'm going to be doing the mathematical equivalent of starting at the ground level, arguing about wires, except it's math. And the level of formality and the level of detail that I'm going to go into at the beginning is significantly higher and therefore, significantly more boring than we will normally do in the rest of the semester. But there's an important reason for wanting to do this that's related to the reason why in computer engineering we start with here's the basic physics of what's going on. Let's build up to larger and larger layers of abstraction. Is that the intuition and the skills and the muscle memory you get from reasoning about the lower levels of abstraction help you as you climb the ladder. Later in the semester, we're going to just be claiming things about strings, and we need to know that those things that we claim are true. And the only way that we can know those things are true, really, is by saying, oh, can I prove that by induction? Okay, yeah, this is what the proof would kind of look like. So I'm going to start really, really basic and build up. And some of this basic stuff we'll practice in the lab sections tomorrow. Some of it shows up already in one of the problems in homework 0. And you'll see it again in homework 1. Some of it will show up on the exams. So there are a couple of quotes on the lecture note page that I like here. The one at the bottom, Hilbert, who's one of the people who really, at the beginning of the 20th century, decided, we need to figure out how to make math formal. We need to put it on a firm, formal foundation as opposed to, well, at this point we wave our hands, which is pretty much how all math worked prior to about 1900. If you really look at Euclid closely, those aren't proofs. That's massive hand waving. And what Hilbert said is, math is just a meaningless game played with meaningless symbols on paper, which is actually a fairly accurate description of computation. What we do on a computer, as far as the computer is concerned, is we move bits around according to some instruction that are encoded with bits that don't mean anything. They don't have any semantics as far as the computer is concerned. And at some level, we also have to adopt that attitude. We all know what it means to concatenate two strings intuitively. But if we want to actually argue about it, we have to be dumb. We have to pretend this is a game that we're playing and we're just following the rules. The other one, really the origin of, I think, computer science, or the pre-origin, is Gottfried Leibniz, who you hopefully all know as one of the discoverers of integral and differential calculus as a set of notation that we still use. Basically said, it'd be great if we could just come up with a set of symbols and a language that we could use to settle any question at all. And then we could just sit down, write things out very, very carefully in that formal language. And then if we needed to settle a dispute, we'd just sit down and say, calculemus, let us calculate, let's compute. So in order to do that, we have to know what the rules are. We have to know what the rules of this meaningless game are. So what are the rules? I'm going to be talking about strings. So intuitively, a string is a finite sequence of characters or symbols. What's a symbol? Right? What's a symbol? Anything? Anyone? I'm sorry? Focus. Focus. Generally speaking, when something is called autofocus, you'd think it would be automatic. What's a symbol? Anything. Anything you want. So the way we sort of formalize this is I'm going to pick a set, and I'm going to call it sigma. And this is any finite set. Okay, you can generalize some of the things we're doing to infinite alphabets like the integers, but generally speaking, I'm not going to, because when we really get down to implementing things on a real computer, this set has two elements, 0 and 1. And this set is called the alphabet, and the elements of this set are called symbols. Okay? So the set of people in this room is an alphabet, and I'm a symbol. Or the set of fingers on my right hand is an alphabet, and my thumb is a symbol. Or the integers from 0 to 10 is an alphabet, and the number 8 is a symbol. We just fixed that in advance. Okay? So a string, formally, I'm going to be very, very formally, is one of two things. It's either a special thing which we write as epsilon called the empty string, or it's an ordered pair where A is a symbol and X is a string. And I have to be very careful here. This is a symbol in my fixed alphabet, and this is a string over that fixed alphabet, and what I'm defining is a string over that alphabet. So a binary string, a string of bits, is either nothing, or it's an ordered pair consisting of a bit and a string of bits. Right, now this is, this is the, canonical example of a recursive definition. Right, it seems to be circular, but it isn't. Right, intuitively, and I really mean this, it's just intuitive at the moment, it's not formal yet. What you're doing is you're defining strings essentially as some sort of process that proceeds recursively that either terminates by saying, okay, I'm done, the empty string, or it says, okay, I'm going to write down the letter A, and then I'm going to recursively keep writing down the string. Right? I insist that every string eventually terminates, that this recursion eventually bottoms out. Okay? So a good example of a string is this, right? It's an ordered pair whose first element is the letter S and whose second element is a string, whose first element is the letter T and whose second element is a string, blah, 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 whose first element is the letter G and whose second element is the empty string. Now, for the sake of sanity, generally when we write down strings, we leave out all the syntactic sugar. The parentheses and the commas and the epsilon at the end, that's syntactic sugar to allow us to think about these things formally. Generally, I'm just going to write down the sequence of characters juxtaposed against each other, unless the string is empty, and then I'll write down an epsilon. Okay? But you should always keep in the back of your mind, this informal notation that you're used to is really just shorthand for this more complicated sequence of nested shortest pairs. How many of you have ever played with any dialect of Lisp? Oh, that's sad. Those of you who are CS majors will see this in 421. Everything in Lisp is made up of lists, and a list is an atom followed by a list, or it's the special symbol nil. It's exactly the same thing. And when I say any dialect of Lisp, how many have customized your Emacs profiles? Anyone at all? Oh, man. I think this is the point where I'm supposed to say, get off my lawn. Lisp is cool. I'm one of those strange people who, I've been talked out of it for reasons of otherwise I'd tear my hair out. But, I'm of the opinion that Lisp ought to be the first thing that you see because nobody knows anything. And then you, walking in the door, everybody's on a level playing field. And everything has to be done with recursion. So when you come into this room, everybody goes, yeah, we know. So I guess we're going to be teaching you a little bit of Lisp. Okay. Now, generally, again, the way we would normally write this is, a string W is either epsilon, just a special symbol that means nothing, or it's AX, where A is a symbol and X is a string. Okay, again, this is just shorthand for that formal ordered pair notation. Sometimes, if we want to make this really clear, we might put a little dot between the A and the X. This is just like multiplication in algebra. Sometimes we have the dot, sometimes we don't. It depends on whether it makes things clear or not. Okay? Now, occasionally I need to refer to, the set of all strings, except I can't do that because I have to specify an alphabet. So I'm going to use this symbol sigma star. That means the set of all strings over sigma. Now, sigma star is an infinite set, right? This is an infinite set. But I need to make this very clear. Every string in this set is finite. This is an infinite set containing finite things. It's kind of like, if you want to think of it by analogy, it's kind of like the set of integers. Every integer is finite. Infinity is not an integer. Infinity is not a number at all. But the set of all integers is infinite. Okay? String. Z. Okay? Now, talking about the set of all strings, maybe, there's some strings and we have a set for them. Maybe the thing that I ought to start with is defining something simple. What's the length of a string? And I'm going to use the absolute value notation to denote length. This is the same notation that people use often to denote, the number of elements of a set. Okay? So I'm going to define this function formally. You all know what it means, but pretend for the moment that you don't. The length of a string is defined to be one of two things. Now, the two cases of the definition correspond to the two cases in the definition of a string. If it's a string, it's either empty or it isn't. And what I mean here is, right, either W is epsilon, the empty string, or it has a first symbol, A, and the rest of the string we'll call X. Hey, this is just by the definitions. So perhaps you can tell me what I should put into these two cases. What is the length of the empty string? 0. Good. And what is the length of the non-empty string, or any non-empty string? 1 plus the length of X. That's it, right? Now, notice this recursive definition follows the recursive definition of strings, and it does so in a way that immediately translates into a recursive algorithm. This is simultaneously how you would define length and how you could compute length, right? You say, is the string empty? Yes, return 0. No, add 1 to the length of the tail of the string, what you get when you take off the first character. Good. All right, so let's try something slightly more complicated then. Concatenation. Okay, so intuitively, I want to be able to say something like, if I concatenate now and here, I get nowhere. Okay? This is the intuition. You all know what this means. Concatenate means write down the first string and then write down the second. Except that the words write down don't mean anything. We have to do everything in terms of the language that we're developing. So let's take the concatenation of two strings x and y. I'm going to represent this by a slightly larger dot, because I'm defining a new function that's different from that little dot that I talked about before. In practice, again, a lot of the time we'll just ignore the dot, but since we're being extra careful and extra formal, I'm going to put it in for now. Okay? So, the concatenation of two strings, again, the definition has two cases. Anyone want to guess what those two cases are? Yeah. Okay, either x is empty, or x is some character A followed by some other string. Okay? A is a symbol, Z is another string. Okay? Good. So what is the definition of x concat y when x is empty? What do you get when you add nothing onto a string? The same string. All right, now for the slightly more interesting one. Okay, suppose the string isn't empty. What's the definition of x concat y? And then, so this is the example up here at the top of the page. X here is the string now. A, the first symbol, is n. Z, the tail of the string, is ow. I somehow want to write now concat here as in terms of n, ow, and here. Yeah. Right. What's the first character in x concat y? Hey. What's the rest of x concat y? Z, right. Z concat y. Oh, sorry. Yes, that's right. Okay? Now, in some ways, again, this looks like we're playing little, games with symbols, and, well, we are, but we're doing this in a way that we can be very, very careful and get used to recognizing what we have to prove. I mean, another way that you could write this definition is by just declaring essentially that these dots are associative, okay? Except that's not really true because they're not really the same dot, okay? But as intuition goes, it serves you pretty well. Okay, now let me start now with the first thing that I might want to prove about concatenation. Okay, now, by definition, concatenating the empty string on the front of something else gives you that something else. I want to prove that that also works in the other direction. Concatenating the empty string on the end of another string doesn't do anything to that string. And of course, this is obvious. There are no characters to glue on. There are no new symbols being introduced. What else could it be? But I partly want to show this as to expose the boilerplate structure of the kinds of proofs that I want. So first, I'm going to go once again quickly through the boilerplate, exactly in parallel with the stuff that we saw in section yesterday. So I'm gonna think about a slightly different theorem because I deliberately want you not to know what the theorem means. And I want to show you how much of the proof you can write without knowing anything about the meaning of the theorem. And this really is the attitude that you should take. Okay, so I'm going to imagine that I want to prove that every string is perfectly cromulent, whatever that means. So what is the first step? What do I do first? Out of your sensei. The beginning of the theorem is every string. So immediately, having read those two words and nothing else, I write down, let W be an arbitrary string. And then I read the rest of the theorem. That string is perfectly cromulent. And so I know what the conclusion of the proof is going to be. W is perfectly cromulent. I can write that down now. I know nothing about what perfectly cromulent means. I know, actually, now I don't even really know what a string, I don't even have to know what a string is at this point, right? Every substitute teacher is perfectly cromulent. Okay, let W be an arbitrary substitute teacher. We conclude that W is perfectly cromulent. Okay? Now, I'm probably going to prove this by induction because that's the kind of class this is. So the next step is let's write down the induction hypothesis. And whenever you're proving things about strings by induction, the induction hypothesis is assume all shorter strings work. Okay? If you want to think of it this way, I'm doing induction on the length of the string. But notice I'm doing strong induction on the length of the string. This is basically the most powerful induction hypothesis I could possibly assume, but I can safely assume this and get a formally correct inductive proof. So again, the form of the induction hypothesis is purely mechanical. I'm proving something about strings, so I know the first half of the induction hypothesis is going to be about all strings shorter than W. And the second half of the string the second half of the induction hypothesis is essentially going to be a statement that says the theorem applies to those shorter strings, right? But never say literally Assume for all shorter strings that the theorem holds. Always write it out, because the theorem doesn't actually refer to x, right? Do the transcription. Write it out by hand. Later, when we're more comfortable with doing this sort of thing, you know, we'll be able to sort of safely assume that you know what I mean when I write down, okay, the induction hypothesis. But for now, always write it down and always write it down explicitly. Now, the next thing I need to do is write down a skeleton for the case analysis. And at the moment, because the only word in this theorem whose definition I actually know is string, the only case analysis I can imagine is one that is based on the definition of string. And the definition of string has two cases. Either it's empty or it's a character followed by a string. And so my case skeleton is going to have two cases. The first case is, suppose the string is empty. And the conclusion of that case, I know, is going to be, therefore, W is perfectly cromulent. So I might as well write that in now. And the second case is going to be, suppose W is not empty, then it's equal to AX for some symbol A and some string X. And at this point, I know that the induction hypothesis can tell me something about X, because X is shorter than X is shorter than W by the definition of length. And so I know at this point the induction hypothesis implies that X is perfectly cromulent. And again, at the bottom of case 2, I can write what case 2 is trying to prove. And now I've reduced the problem of proving all strings are perfectly cromulent to two simpler cases. One, prove that the empty string is perfectly cromulent, and two, prove that a string that starts with the letter A and the rest of the string is perfectly cromulent is perfectly cromulent. And then at this point, basically I'm going to start chasing definitions. I need to know the definition of perfectly cromulent now. And so I can't really provide any more details in the proof because I don't know what that phrase means. But up to this point, I don't care, right? I'm recommending that when you try to prove things about strings, you write this boilerplate down for the same reason that when you're learning to play the piano, your piano teacher tells you to practice scales. You want to get the action of putting your fingers on the keyboard to be in your muscles, not in your brain, so that you can get out, you can take your attention away from the mechanics of playing the piano and get into the actual creative part of playing the piano. The same is true here. I want you to write these things down so that the mechanical parts of writing down induction proof are in your hands, not in your brain, so that you can free up your brain to do other things. Okay? So, here is this thing that I want to prove. Let me go through, oh, come on, autofocus. Actually focus. Let me walk through, how to prove this, okay? So, proof. Step 1, bow to your sensei. W be an arbitrary string. Thus, W cat E is equal to W. Okay? Step 2, write down the induction hypothesis. Assume for all strings X, where X is shorter than W, that X concat epsilon is X. Okay? Need another color, green, good. Step 3, there are two cases to consider. Case 1, W is empty. Case 2, W is equal to AX for some character A and some shorter string X. And I can write down immediately the induction hypothesis implies that X dot epsilon is equal to X. At this point, I can start to think. Okay? Let's think about case 1, what I need to prove in this block. I want to prove that W dot epsilon is equal to W, and in this particular case, W is epsilon, so I need to prove that epsilon dot epsilon is equal to epsilon. Can somebody give me the one-line proof? Why is that true? By definition. Okay? This is by definition of concatenation. Epsilon dot anything is anything. And in this particular case, that anything is the empty string, but okay, fine. Okay? So now if I wanted to be really pedantic about this, and well, I do, would fill in a couple of steps here. W dot epsilon, which is the thing I'm trying to prove something about, it's equal to epsilon dot epsilon by assumption. That's equal to epsilon by definition of dot, and that's equal to W by assumption. Okay, so the second case is suppose, and I'm going to flesh this out here because it's going to take a little bit more room. Suppose W starts with the letter A and ends with the string X with the property that if you add epsilon to it, it's still X. Okay, so I'm going to start by saying, here's the thing I want to prove something about. Based on what's written on the paper, what can I conclude immediately about W dot epsilon? Sorry? No, that's what I'm trying to prove. I can't conclude the theorem. I mean, mechanically, simply, stupidly, you're thinking, you're trying to be clever, that's bad. I'm going to say this all semester long. You're being clever, stop it. What is actually written, what fact about W is actually written on the page? Good. So W dot epsilon is AX dot epsilon. Right? Good. Now, what do I know about AX dot epsilon? From the definition. It's the same as A dot X dot epsilon by the definition of not. Now, what do I know about X dot epsilon that's written on the page? It's equal to X. Right? By the induction hypothesis. And what do I know about A dot X? Yeah, it's equal to W by assumption. And so now the proof is done. Okay. Now this is a fairly standard series of events when you're developing this proof. You write down something on the left side of an equation that you want to prove, and you can say, what is on the page or in my set of definitions that I can immediately conclude about this thing that I've just written down? Well, the only thing I conclude at the beginning is, well, I'm in case 2. And then, oh, that looks like case 2 of the definition of dot. And oh, that looks like the induction hypothesis. And oh, that looks like I'm in case 2. Every one of these steps is mechanical and stupid. I'm just turning the crank. Okay? But it's important to actually do this because it is surprisingly easy to convince yourself of things that look obvious and are not. Whenever I read an actual paper, not just when I read homework, whenever I read a paper and I see that the author claims that something is obvious, I immediately assume that it's wrong. because at least 3 times when I have written a paper where I claimed something was obvious, I discovered a few years later that it was wrong. It's a little embarrassing, but at least I was the one that figured it out and not someone else. So let's try something else. A slightly more interesting claim. If I concatenate 2 strings, then I add their lengths. Okay? All right, we know this is true, but let's walk through the proof. All right. So, proof. Now I've got 2 strings here. Any 2 strings, W and X. So what is the first line of the proof? Let W and X be arbitrary strings. And what's the last line of the proof? So W not X, the length is length of W plus length of X. Okay, good. Now I'm probably going to prove this by induction. I have to break out of my purely mechanical mindset for a small moment and ask, induction on what? I've got 2 things. Well, eventually I want to be able to express that thing on the left, you know, the length of W dot X recursively in terms of something else. So the right thing for me to do is maybe refer back to my definitions. Well, if I refer back to the length, I'm going to need to know something about the first character of the concatenation. And, well, if I look at the definition of concatenation, I can tell something about the first character by looking at the first character of the string on the left. If I imagine actually trying to compute this thing, the definitions don't change the string on the right. They only change the string on the left when I recurse. And so that's a hint that I should do induction on W, not on X. And so my induction hypothesis is going to be assume for all strings, I can't call it X, so I have to go to the next letter, where Y is less than W, that we have Y dot X has length, length of Y plus length of X. Okay. I'm only doing induction on W. I'm not doing induction on X. This is one of the reasons why bow to your sensei is the first line. Before I know anything about how I'm going to do the proof, I can immediately say, I have to fix W and X. But in this particular case, I'm only going to be doing induction on one side, and I'm never going to change X. I'm never going to look at a smaller thing of X and ask the recursion fairy what to do. Yeah?
Can you explain why you chose or Y again?
I needed a letter. X was taken.
So why did you choose to induct on Y instead of X?
I didn't choose to induct on Y. Okay, why did I choose to induct on W? If I look at the recursive definitions here, the recursive definition of concatenation, there are 2 strings. In this case, they're called X and Y instead of W and X, but there are 2 strings, one on the left and one on the right. If I look at how I recurse, the recursive call uses a shorter first string, but it uses the same second string. So as I go down in the natural recursive structure, the first string is the thing that's shrinking. That's why I wanted to recurse on that, the first string and not the second. And the second string, notice, doesn't change, which is why when I write down the induction hypothesis, You'll notice this, I get the same string x here in the induction hypothesis. I could also say, for all strings y that are shorter than w, and for all strings z, y.z has the length that I expect it to be. But that's stronger than I really am going to end up needing. It would be perfectly fine. It's just more than I need. Okay? So the form of the induction hypothesis itself sometimes depends on the definition of the thing we want to prove something about. Okay? Now, again, I'm going to have two cases. Am I going to have two cases? Well, maybe I'll have two cases. Ah, that's what's wrong. Yes, I'm going to have two cases. Okay? So case one, W is the empty string. In case two, W is something in the form AY, where A is a symbol and Y is a string. I deliberately chose the same letter Y there to make it clear that where the induction hypothesis is going to kick in. Okay? So at this point, I want to write down, what I want to prove something about. And now, mechanically, I want to do substitution and definition chasing and induction hypothesis substitution to figure out what this is. So w.x, in the case where w is epsilon, what is the length of w.x equal to, mechanically? The length of epsilon.x, because w is epsilon. Small steps, right? I know that you know the answer because it's written right here, right? There's this funny thing about writing proofs. At one level, if you're asked to prove something, it's really a lot easier to prove it if you know that the thing you're trying to prove is true. This is the thing that makes research so wonderful. You try to prove things and you don't know whether they're true or not, right? But saying, oh, I heard somebody else prove this already, just that statement by itself makes it psychologically easier to prove, right, to come up with your own proof. On the other hand, knowing that the theorem is true is distracting because you think, I could just jump ahead because I know the theorem is true. And you have to refrain from doing that. While we're inside this proof, this statement at the top of the page is intuition. It's not a fact. We're trying to establish that fact. Okay, anything I know about the length of epsilon.x that I can substitute in mechanically now? It's the length of x by the definition of dot, right? The definition of concatenation says epsilon concat anything is that anything. The fact that I've got absolute value signs around it doesn't matter. I'm just doing, find and replace here. Now, in the other direction, eventually I'm aiming for this. And I'm deliberately writing this at the bottom of the page, and now I'm going to try to reason backwards to meet in the middle. What I do not recommend is writing U-shaped proofs. I want to prove that this is equal to that. Well, I know this is equal to this prime, and I know that is equal to that prime. So now I want to prove that this prime is equal to that prime. That thing you learned in high school algebra class, take those neurons and dash them out of your brain and throw them in the trash. Do not do that. If you want to write a U-shaped proof, it's fine if you want to write the statements in that order. Just stretch the U down to the bottom of the page. Okay? So, is there anything I can claim immediately about this expression, length of W plus length of X? Well, yeah, it's the length of epsilon plus the length of X. And now what can I do now? Well, yeah, this is 0 plus the length of X. So here I'm using the definition of length. Here I'm using the assumption about what case I'm in. And in the middle there, I'm assuming that 0 is the additive identity, and let's assume you know that. Okay. What about the second case? W is equal to A dot Y. All right, so again, what can I conclude mechanically about the length of W dot X? I substitute AY for W. Right? At this point, what can I conclude about the length of AY dot X? What does the definition of dot tell me this is? Okay? Now, what's next? Right, this is 1 plus the length of y dot x by, definition of length. Okay. Now what? Now, y dot x is in exactly the right form to apply the induction hypothesis. So this is 1 plus absolute value y plus absolute value of x. Now, eventually, remember, we're trying to get to this. So maybe now is a good point to start walking backwards. Anything I can conclude about this expression? Yeah. This is the length of AY plus the length of X. All right. And now we're done. These two lines of reasoning sort of click together because the third to the bottom line implies the second to the bottom line by definition of length. Okay? So ultimately, everything boils down to the definition of concatenation or the definition of length, or the induction hypothesis. Okay? So everything is set up the infrastructure, and then what can I conclude mechanically? What can I conclude mechanically? I seem to, right at the point where you apply the induction hypothesis, it's usually a good time to start at the end and try to walk your way backwards to meet yourself in the middle. All right. When you're really doing this in practice, it doesn't really matter what order you write these lines in. You could say, well, I'm pretty sure I'm just going to guess that some line is going to show up in the middle of this derivation. I don't know how to get to it mechanically, and I don't know how to get to the conclusion mechanically from this statement just yet, but I'm pretty sure this line is going to show up in the middle. So go ahead and write it in the middle, and then walk your way backwards and forwards from there. That's fine. As long as in the end, what you present to the reader is a sequence of logical steps where every single step is, oh yeah, that's just by definition, by definition, by definition, by the induction hypothesis, by definition, because I'm in case 3. There was a hand up somewhere. Yes? Thank you for the sea anemone.
Can you explain what U-shape is and how that's
Okay, so a U-shaped proof is one so do not do this. I can't even. Let's see. So, I could do something like, I want to prove that 5 plus 1 squared is equal to 5 squared plus 2 times 5 plus 1. Right? And so, well, this is equal to 6, so I get 6 squared, and this is equal to 25 plus 10 plus 11. And, well, this is 36, and this is 36, and so I'm done. And so when I say U-shaped proof, what I mean is the actual logical flow of the proof is like this. Right? But what's actually written on the paper is, at the top line, you've written the thing you want to prove. And then, step by step, you've derived the theorem 36 equals 36. That's not what you want to do. You want to start by assuming things you already know to be true and end with the thing you're trying to prove that's new. Right? So the right way to write this sort of sequence of derivations is to say, 5 plus 1 squared equals 6 squared equals 36 equals 25 plus 10 plus 1 equals 5 squared plus 2 times 5 plus 1. Every one of these steps on the left follows mechanically from the one above it. And so I want to prove that A equals B. I prove A equals C equals D equals E equals D equals Z equals A equals B. Right? Every single step is mechanical, and it flows in the right direction. Whereas what you've written over here in this U-shaped proof is you started out by writing down the thing you want to prove and end up proving something that you already believe to be true. Now, there are any number of examples of proofs where you can do this and derive that 1 equals 2 or 0 equals 1. And people go, it's a paradox, because at some point you took a square root in the wrong way. The real reason that this paradox arises is because you were doing something that isn't even approximately in the form of a proof to begin with. So of course it's going to screw up. Right? If somebody asks you to write a piece of C code, you can't give them Python. If somebody asks you to prove something, you can't give them U-shaped argument. That's not a proof. Okay? Okay. All right. Let me mention that once you've established a few simple things like this, it's not hard to look at more general things. So I'm not going to actually walk through the proof here in class. But it's helpful to sort of walk through the proof in the notes to show that concatenation is, among other things, associative. Right? It doesn't matter what order you glue things together, as long as, it doesn't matter whether you glue this pair first and then that one. As long as, in the end, the characters end up in the same sequence. Now, the proof is, well, here it is in the notes. And you can see the proof begins with let w, x, and y be arbitrary strings, and then there's the statement in the induction hypothesis. And again, I'm only doing induction on W, and then there are only two cases, and for each case, there's, because I'm in that case, and by definition, and somewhere in the middle here, there's a by the inductive hypothesis. Okay. Once you've established that concatenation is associative, this opens up other possible structures for inductive proofs about strings. So, for example, well, there's a second proof of the same theorem in the notes that has 3 cases instead of 2. That basically uses a slightly different recursive structure. Instead of saying that a string is either nothing or a character followed by a string, another recursive structure that you could exploit is the following. A string is either nothing, a single character, or 2 strings concatenated together. And it gives you 3 cases instead of 2, but the nice thing about this is then you're not always forced to try to take the first character off when you recurse. You can break the string into smaller pieces in the middle, and sometimes that's actually a much more natural thing. In this case, the proof is longer, but mostly it's longer because I have more cases, not because it's actually any of the cases is more complicated. Yes?
Why do you have the third case where it's just a single character?
Well, think about doing recursion on a string, where I say, okay, either it's empty, or I break the string into 2 smaller substrings and recurse on each side.
So an empty string doesn't count as a smaller substring?
Well, it does, but the other side isn't smaller.
Okay.
Right? If you're doing merge sort, for example, you split your array into 2 smaller subarrays. That doesn't work if your array has length 1. So you have to handle that case separately. So I mentioned this in the lab section yesterday. When you're going through the case analysis, you have to be really careful to make sure you're not making any additional assumptions about when your recursion will work. If it turns out that you need n, the size of your string, to be at least 5 in order to split it into 6 pieces, okay, then 1, 2, 3, and 4 are also going to be base cases that you have to handle directly. Okay? All right. So in the notes, there are a bunch of other things that a couple of other things that I define and prove. One thing that I want to mention briefly is this notation. Auto. This is the standard array notation that I will use when I'm talking about pseudocode. I have an array W, and it has characters from 1 to n. And when I want to think, so this is a string or a sequence or an array, and I'll write W of I to mean the ith symbol or entry or element of this sequence. And this notation has a formal definition, which is, what you would expect. So W of I is either A, if I equals 1 and W equals AX, or it's X sub I minus 1 if I is greater than 1 and W is equal to AX. You'll notice that it's not defined when the string is empty, because that index has to be something between 1 and its length. Yeah?
Is the array 1 indexed?
The array is 1 indexed in this case. Fine. You want 0 indexed arrays? Great. We want 0 indexed arrays, we can do 0 indexed arrays. It's just a question of how you want to define it. 0, 0, 0. Okay? Simple change to the definition. In fact, really what I ought to be defining is W from I to J. You can use whatever index range you want. Okay? Okay? So this is a typographical convention. The way that mathematicians would normally write this is W sub I. The way that we write this when we're writing code is W bracket I. These are synonyms. They mean exactly the same thing. And the reason why we use brackets is because there is no subscript key on a typewriter. That's it. That's why. Okay? There's no difference between these two symbols, except that one looks more mathy and the other one looks more like code, because despite the advent of Unicode, which does support subscripts, we don't have subscripts in our code. Right? Otherwise, no difference at all. Okay, so much for individual strings. Are there any questions about either hopefully not about the things that we proved or about the definitions themselves, but about the kind of argument structure, in proof boilerplate that I'm advocating here? And we'll get lots of chances to practice with this, okay. All right. Yeah?
Just wondering if it's not specifically mentioned, can we assume the arrays are 1 indexed?
I will always specifically mention. Whenever I want to talk about an array, the way that I will indicate they're being given an array is I will write A, open bracket, 1 dot dot n, close bracket, declaring that it's 1 indexed. Or I'll write A, 0 dot dot n minus 1, close bracket, indicating that it's 0 based. Or I'll write A, I dot dot j, indicating that the range is from I to j. Right? I will always be explicit about this. If it matters, just write, I'm using 0 indexed arrays. If it doesn't matter, don't. Yeah?
It looks like you declared A as an arbitrary
So if I'm really being careful, and thank you for pointing this out, I should write here for some symbol A and some string Y, and if I want to be even more formal, I would say before I did this line, or I applied the induction hypothesis, I would say by the definition of length, the length of W is one more than the length of X, and therefore one more than the length of Y, and therefore the length of Y is less than the length of W, and therefore I can apply the induction hypothesis. At some point, we have to raise the level of abstraction a little bit. Okay? But you're absolutely right in terms of what I want you to do when you're declaring your variables. Yeah, you should write that down, and I apologize for missing that. Is the proof perfect otherwise? Okay, good. All right. Now, the next thing that the next technical term that I want to talk about, and I'm not going to say very much about this because we only have 10 minutes, and one of the lessons that has been hammered into my head is if I find myself thinking, oh, I have one more technical thing to say, and oh, I've got 10 minutes, I can do it. I can't. But this will be relatively simple. It's just a definition, but I want to make sure that and a bit of notation, but I want to make sure that we're all on the same page. A language is a set of strings. Okay? Normally, when we talk about languages, we don't just mean a set of strings. English as a language has additional structure to it. It has sentences and paragraphs and serial commas and semicolons and rules about when you capitalize and when you use he and she and when you put S's on the ends of things and apostrophes before those S's. When I talk about English as a language in terms of a formal language that we might prove something about, I mean the set of words in the OED, perhaps. Right? Each of those words is a string, and that's it. There's no additional structure about how these words can be glued together. There may be no notion of gluing together at all. Okay? So a good example of a set of strings is sigma star. This is the set of all strings over the alphabet sigma. So in particular, if I say 0, 1 star, this is the set of all strings of zeros and ones, including the empty string of zeros and ones. Okay? Here's another string, or sorry, here's another language. It's the empty set. Finally, here's another language, the set containing the empty string. Okay? These are not the same thing. And neither of these is the same thing as the empty string. Okay? So, I really want people to be careful about this. That O with a slash through it, so it represents the empty set. That is the set that has no elements. We saw this in lab yesterday when we talked about the empty set of powers of 2. If you're typesetting this, that is not the Greek letter phi. Okay? This is, in LaTeX, var nothing, or empty set. I prefer var nothing because the circle looks like a circle. Here, empty set, it looks like a 0. This symbol has never been the Greek letter F. It has always been an O with a slash through it. It was first used in the late 1800s by Nicolas Bourbaki, who is the pseudonym of a collection of French mathematicians who decided they wanted to do everything formally, and they needed a notation for nothing. And so they chose an O with a slash through it, which is a letter in the Danish and Norwegian alphabet that's roughly pronounced Okay? It's the equivalent of an O umlaut in German. Okay? I will teach you the most important word in the Danish language. Beer. Okay. It's not a fee. Don't call it fee. Don't call it phi. If you must call it by its name, call it but if really it's the empty set, just call it the empty set. Now that second symbol, the one with the braces at the little epsilon inside of it, epsilon is really a mnemonic for empty, but it's the empty string. It's still nothing, but it's a different flavor of nothing. It's the kind of nothing that you concatenate onto other strings. You can't concatenate the empty set onto a string for the same reason that you can't add an integer to a cat. It's just the wrong type. Or if you've taken any physics courses, you never add seconds to meters. You just don't. If you find yourself adding seconds to meters, something is wrong. Similarly here, if you find yourself trying to concatenate a string to a set, something's wrong. Okay? So this thing in braces, this is not an empty set. This is a set that contains one element. And that element has a type string, and that string has no characters in it. Okay? So these three things are these three things are different. Don't mix them up. Okay? But you can talk about, other kinds of other kinds of languages. You could say, the set of all strings in 0, 1 star, whose length is prime, and that have 2 to the n zeros for some integer n. Right? So this is a language. It's a set of strings. Okay? The set of all Python programs that always halt. This is a language. Okay? A Python program is a string. It's a string over, roughly speaking, the ASCII, the 128 element, minus the, let's say 96 element printable part of the ASCII code. Okay? And is a well-defined sense in what it means for a Python program to halt on every input. And so this is a perfectly good definition of a language. Okay? So when we start talking about different kinds of languages, we're going to start in the next lecture building languages from smaller things, right? So the sort of canonical for some string W, the sort of canonical language that we might want to build things out of are the sets that contain one string, singleton sets. And then if A and B are languages, then we can talk about the union of those languages, or the intersection, or the complement, meaning everything in sigma star except the things in A. We can do other things with languages, like I can define the concatenation of two languages to be what you get when you concatenate an arbitrary string from the first language and an arbitrary string with the second. Okay? So, for example, I can define the set of words whose first half comes from Greek and the second half comes from Latin. And this is a non-empty set of English words, actually. All right, so you can get things by unioning sets the way you would normally do. You can get new languages by concatenating other languages. And then there's one last thing, which we'll talk about in detail next time. This is the star of a language. This is what you get by taking repetition. So I can take any number of strings from the set A and concatenate them together. And this gives me a new string that's an A star. So in particular, even if A doesn't contain the empty string, A star does, because the empty string is a concatenation of 0 elements of A. Okay? I'm going to hold off on giving the formal definition of this thing, but I will leave as a problem to figure out what is the correct way of pronouncing the name of the guy who came up with this symbolism. If there are no questions, I'll see you tomorrow. Thank you.